Welcome, university students, to today's exclusive masterclass. Now, we're not just doing a standard explainer today. Oh no, we are embarking on a really rigorous academic journey straight into the heart of the Bayesian school of thought. This is where probability stops being about, mere random chance, and actually becomes about updating our own beliefs with new evidence. So let's dive right in.
Here's a quick look at our roadmap for the session. We'll cover the foundation of conditional probability, jump into a practical CARS case, explore the multiplication rule, tackle independence versus dependence, break down total probability, and then wrap it all up with a Bayesian summary.
All right, let's kick things off with part one, the foundation of conditional probability.
So, grasping conditional probability really requires a shift in your mindset. We are no longer looking at the entire universe of possibilities. Instead, we're looking at a reality that's been restricted by prior events. Take a look at the formal definition here. We read this as the probability of A given B. But I want you to ask yourself, why are we dividing by the probability of B? Well, think about it logically. It's because B has already happened. Event B is literally our brand new universe. So we take the intersection, that specific space where A and B overlap, and we divide it by our new restricted reality, B. And of course, if the probability of B is 0, well, the restriction makes absolutely no sense because it never could have happened in the first place.
Moving right along to part two, let's put this into practice with the CARS case. Formulas are great and all, but let's actually ground this abstract math in reality. What you're seeing is a raw data matrix showing a lot of 50 cars at a dealership. As you can see, some are for the internal market, some are for export, some are white, and some are blue. Now imagine the manager randomly selects a white car. Stop right there. I want you to focus your attention completely on the restricted universe of just the white cars. We literally do not care about that grand total of 50 cars anymore. Our entire world has shrunk down to only those 20 white ones. Let me walk you step by step through calculating the actual probability that this randomly selected white car is an export model. Step 1. The unconditional probability of selecting a white car from the whole lot is 20 out of 50, or 0.4. Step 2. The probability of a car being both white and for export is 10 out of 50, or 0.2. Finally, step 3. We just apply our formula. We divide the intersection, 0.2, by our restricted universe of white cars, which is 0.4, and the result, 0.5. The math logically sequences together to reveal a clean 50% chance. Stepping it up a notch now, with part 3, the escalation into the multiplication rule and urns. Okay, so what happens when events occur sequentially, one right after another? Let's break down this algebraic derivation. If you take that conditional probability formula from earlier and simply multiply both sides by the denominator, you get this truly beautiful relationship. The probability of A intersection B equals the probability of A times the conditional probability of B given A. This brilliantly shows how conditional probability allows us to calculate the exact intersection of two dependent sequential events. To really master this concept, let's walk through the classic urns and colored spheres example. Imagine drawing colored spheres from a sequence of bags, physically moving them from one to the next. Notice how this tree diagram visually maps out that step-based sequential logic. Every single time you move down a branch, the probabilities change. Why? Because the universe of remaining spheres has literally been altered by your previous action. To find the final outcome of any specific path, you just multiply the probabilities along those connected branches. Which brings us perfectly to part 4, independence versus dependence. So think about this. What actually happens to our universe of possibilities if we extract a sphere from an urn and put it back versus keeping it out? This draws a stark, really memorable contrast. If you replace the item, the universe resets perfectly. That next draw absolutely does not care what happened before. That right there is the definition of independence. But if you do not replace it, well, the next draw is fundamentally altered by the first. The numbers have physically changed. That is dependence. Guys, this distinction is absolutely crucial. It's a critical learning objective for literally any real-world statistical application or data model you're ever going to build.
And here we are at part 5, the grand finale, total probability and Bayes.
All right, so how do we navigate a fully partitioned sample space to find an overarching truth? Let's set up a classic objective scenario to really test your analytical skills. Picture this. A fugitive escapes and flees down one of 5 distinct paths. He can only choose one path, meaning these paths are mutually exclusive. They form a perfect partition of our sample space. Now, we know the probability of him choosing each path, and we also know the police's conditional probability of catching him on each specific path. I want you to think about how you'd solve this before we break it down. How do you find the absolute total probability of his capture?
Well, here is the analytical breakdown. First, you partition your sample space into those 5 distinct paths, C1 through C5. Then you assign the initial independent probability of the fugitive choosing each individual path. Next, you identify the conditional probability of capture given that specific path was taken. And finally, the magic step. You multiply the probability of taking a path by its conditional capture rate, and you just sum up all those products. You are mathematically gathering up all the different mutually exclusive ways the fugitive could be caught to find the grand total. This is the awesome, almost magical power of total probability.
Finally, part 6, our masterclass summary on the Bayesian perspective. You guys have done fantastic work today. Let's summarize the overarching philosophy here. This is your punchy outline of the critical points of Bayesian statistics. First, remember that conditional probability is not just a mathematical fraction. It is an updated reality based entirely on new evidence. Second, the multiplication rule allows us to decode complex sequential events seamlessly using tree diagrams. Third, always remember that the simple act of replacement fundamentally alters the independence of your variables. And finally, total probability unifies partitioned, mutually exclusive events into a single, comprehensive statistical truth. Listen, these aren't just formulas to memorize for an exam. They are essential, foundational tools for modern data science.
Which leads me to leave you with one final provocative thought. Now that you have the tools, how are you going to use Bayesian logic to update your own beliefs and analyze the massive data universe all around you? Data is constantly changing our restricted reality, and now you know exactly how to measure it. It's been an absolute pleasure guiding you through this explainer today. Keep learning, keep questioning, and I'll catch you next time.